Hi guys, we meet again virtually. Today I want to just put a quick plug out there. I put on the class page, I don't know if anybody noticed it, I did this way back when the shutdown first occurred, but I put the the Best Lent Ever videos on the class page. So if anybody's interested in looking at those videos, they're there for you to look at. All right, let's talk about today's lesson. Today's lesson will focus on specific heat and calorimetry. You might want to get your textbook and calculator because I will be referencing the text and we are going to be doing some math. You should, if you're referencing the text, you should be looking at chapter 6. So calorimetry is the science of measuring heat. For us to make any type of accurate measurements of heat given off or absorbed during a chemical or physical change, we're going to use something called a calorimeter. And you'll see I have a photo of a calorimeter or a picture of a calorimeter on this particular slide. You'll notice it looks very much like a styrofoam cup because it is. The styrofoam cup holds water. The reaction is done in that water. You can notice also there's a thermometer that is inserted through the cover of the calorimeter, and also a stir rod inserted to stir the reaction as it's happening. The calorimeter ends up being filled with water. The walls of the container, because they're styrofoam, are insulated, and this minimizes the exchange of heat that would occur with the air. So we should probably talk about what heat capacity is. Heat capacity is the heat required to raise the temperature of a substance 1 degree C. Notice that we're not taking mass into account here. Sometimes substances might require a lot of heat energy to raise the temperature, and other substances might not need a whole lot. But we can measure this property, and that's the heat capacity. Different substances will have different heat capacities. Identical substances with different masses will have different heat capacities as well. Now there's a variation of heat capacity that's more useful for calculations, and it's called the specific heat. And you'll see on the slide that we have the specific heat definition there. Same as heat capacity, except we've now included mass in the specific heat capacity. So it's the heat required to raise the temperature of 1 gram of substance 1 degree C. And if we needed to calculate the specific heat, we would use this equation. Specific heat is C sub P, and we would need to know the heat. We would need to know the mass, and we would need to know the change in temperature to calculate the specific heat. On page 237 in your textbook, there's a table of specific heats. You will notice that metals have very low specific heats in comparison to water. Water's specific heat is 4.184 joules per gram degree C, and something like aluminum has a specific heat of 0.89 joules per gram degree C. You notice that the water has a much higher specific heat because it takes way more energy to raise the temperature of water than it does to raise the temperature of aluminum. We can also look at this as we've heated the water and now we're going to cool off the water. We've heated the aluminum, we're going to cool off the aluminum. If you think about what you know about water and aluminum, the water is going to take a whole lot more time to cool off than a piece of aluminum foil. So there's a lot more heat or energy being absorbed into the water than into the aluminum. So it makes sense that the water would have a much higher specific heat than the aluminum. But it's always good to remember that metals will always have very low specific heats in comparison to water. We can also talk about molar heat capacity, basically the same thing as specific heat, except we're talking about it in terms of moles instead of in terms of grams. So that's the difference between molar heat capacity and specific heat capacity. So a calorimeter is used to determine the change in enthalpy, or that delta H, in a solution. Since the conditions are constant pressure, we can say that delta H equals Q. So that's something that I want you to keep in mind for the math that we do later in this video. Because energy is conserved, we can also say that the heat released is equal to the heat absorbed by the solution. That's the second bullet point there. And since we know that specific heat equals, let me just write this out for you. Specific heat, we said this on the last slide, equals Q divided by mass times delta T. If we're looking to solve for Q, we can rearrange this equation and end up with the equation that I have off to the left here. Q equals C sub P times mass times delta T. Q is the energy or heat that's absorbed or released by the system. C sub P is the specific heat. I think your book uses S, means the same thing. S for specific heat, or C sub P would be appropriate as well. And sometimes you might just see C, but I think your book uses S. M stands for mass, and T stands for temperature. And when we're talking about delta T, that means that we're taking TF minus TI, or the final temperature minus the initial temperature. And if that delta T is positive, that means the final temperature of our surroundings were warmer than the initial temperature, and so that would be an exothermic reaction. If the delta T is negative, that means our final temperature is lower than our initial temperature, and that means that the surroundings cooled off, and so that means an endothermic reaction. So I just want to make those distinctions for you. Okay, this brings us to our first problem. It is a sample problem out of your textbook. It's on page 239. If you want to pause the video and open your textbook to that page, you can do so now. What I'm going to do is read through the problem, and I'm going to highlight the things that are important, and then we're going to look at what's happening in this particular reaction, and then solve for the enthalpy change. So let's read through the problem. When 1 liter of 1 molar barium nitrate's an aqueous solution, so the only thing that's really important right here is the 1 liter. The amount of barium nitrate's not important because we're just going to be concerned about the mass of the water, and the barium nitrate that is in solution or in that water is not going to change the mass of that water significantly. So we're really only worried about the volume of the water, and we'll convert that to the mass using density. It says it's at 25 degrees C. That's important because we know we're going to be looking at temperature changes here. And we're mixing this with 1 liter of sodium sulfate. Sodium sulfate, again, not going to change the mass of the water significantly, so we're just going to be concerned about the liter that we're using in the calorimeter. Also at 25 degrees C. A white solid forms, and the temperature of the mixture increases to 28.1 degrees C. So we have a temperature increase happening in this calorimeter. It's telling us also that barium sulfate is being formed. So this is a double displacement reaction, solubility rules, all of that stuff. I'm not going to review all of that in this video, but basically what is happening is we have barium ions in solution when it's mixed with sulfate, and these are going to form a solid. So that's what this is saying. Everything is a 1-to-1 ratio. Barium sulfate forms and it's a solid or a precipitate. So that's just a little review of those solubility rules from before, and we do need to know that so that we can calculate the enthalpy in the end. Now it says assuming the calorimeter absorbs a negligible quantity of heat, the C sub P of the solution, we're going to use 4.184 joules per gram degree C. We also know that the density of the final solution is 1 gram per milliliter because, again, the barium and the sodium that's added to the water is not changing the density because it's a very small amount. And we're calculating enthalpy, so that's, whoops, I didn't mean to cross that out. I meant to highlight that and calculate the enthalpy per mole of barium sulfate formed. So we need to know that it's a 1-to-1 ratio going on in that reaction. So that's why I wrote that reaction out. So we know that since the temperature increases, the reaction is exothermic. We know that we have 1 liter of each solution used, so we have a total volume of water at 2 liters. So I'm just going to write that down. I can convert that water volume to grams by converting the liters to milliliters and then multiplying by the density of water. And you can see here that everything cancels but grams. Liters cancel, milliliters cancel, and I'll be left with a mass of water that is 2.0 times 10 to the third grams of water. Okay, that's going to be our mass. So that's going to be important for our calculation. Okay, so there's the first thing that we needed to solve for. The next thing that we can solve for is our delta T. Our final temperature was 28.1 degrees C. We're going to subtract our initial temperature, which was 25 degrees C, to get a delta T of 3.1 degrees C. So that's our delta T, so now we know that. We also said that our C sub P, we're going to use water because the reaction is aqueous, it's done in water. So that's I always use 4.184. That's just out of habit. Your book uses 4.18. Either way, it doesn't matter. You're still going to get a very, very similar answer, if not the same. And that's joules per gram degree C. So now I want to calculate the heat, which is Q. And we're going to use mass C sub P delta T and plug in all of the numbers or values that we have. And we have 2.0. Wow, that was my stomach. I should have eaten breakfast before I did this video. This is grams. I'm going to multiply that by the 4.184 joules per gram degree C, and then multiply that by the delta T, which we said was 3.1 degrees C. Now let's see what cancels here. If I look at what cancels, I have grams canceling, I have degree C canceling, and I'm left with joules, which makes sense because Q should be in joules. So our answer, let me write it in a different color, for Q is going to equal 2.6 times 10 to the fourth joules. Now the question, though, we were asked was, what is delta H, or the change in enthalpy? Well, we know that Q can equal delta H. Q, in this case, we have positive 2.6 times 10 to the fourth because this reaction is exothermic. But we know that delta H for an exothermic reaction has to be negative. So Q, or delta H in this case, I just need to change that sign to negative 2.6 times 10 to the negative fourth, or 10 to the fourth joules. And again, that's just because we know that delta H for this system, because it's exothermic, is negative. If it were endothermic, then we would keep the value of delta H positive, because endothermic delta H is positive. Okay, so just wanted to make that distinction there. And it was asking us enthalpy, so I wanted to talk about that. So that is our first example. Now here on the next slide, we're talking about a constant volume calorimeter. We just finished talking about constant pressure calorimeter, coffee cup calorimeter. This is known as a bomb calorimeter. The reason it's known as a bomb calorimeter is because you put a weighed amount of reactants in a steel container that's inside of a water bath. And you can see in this picture, I'm talking about this container. I'm going to put whatever I'm going to blow up, basically, in that steel container. I'm going to ignite it, and I'm going to determine the delta T so that I can calculate the heat that is given off by whatever I put in that bomb in this water bath. And so the water is going to change temperature, and we'll be able to calculate Q. Now, with constant volume calorimetry, the reaction is, or the equation is not taking into account the C sub P of water, because each of these type of calorimeters will have their own heat capacity. And so all you're going to need to do to figure out the heat absorbed or released is look at the delta T of the water and multiply it by whatever the heat capacity is of the calorimeter. Now, there is an example in your textbook on page 242. I'm not going to take the time to go through each of those steps, but I would like you to try that exercise to make sure that you understand what's going on in the math. Now, if you did not know this before, I'm going to tell you this now. On the class page, I've uploaded the PowerPoints that go along with these videos. So the PowerPoints wouldn't have my voice in them, but you can go back to those PowerPoints and add notes and use them as your notes on your iPad in Notability. And also add in doing these problems. So it's up to you how you want to use those, but they are there for you without the voice. And then you also have the PowerPoint with the voice. I highly recommend using both because it will just help, it will help you study a little bit better. So take some time to do that sample exercise on page 242 and make sure that you understand the steps. Now, if you don't understand the steps, please ask in the forum or email me if you feel more comfortable with that. Either way is fine, and I will answer and explain in that way. So I want to just give you some hints when you're working out these problems. Remember that heat lost is always equal to heat gained. But I want you to think of it in terms of the Q of the system and the Q of the surroundings. So the heat that's lost is equal to the heat gained, but we're going to have a change in sign there. Because as one thing's going up, the other thing is going down. So I want you to think of this in terms of this. So I want you to think of this in terms of the system and the surroundings, where Q of the system equals negative Q of the surroundings. So we're going to have same magnitude but opposite in signs. So what that means is, and I'll write this down here, is that if I put that into the equation that we've been using, mass C sub P times delta T, I'm going to have a negative mass C sub P delta T that I can set these two things equal to each other. And the times where I'm going to be doing this is when I have a calorimeter with the lid on top, thermometer going into the water. Let's just say I want to figure out the heat capacity of a metal. And I'm going to heat up that metal in boiling water. And then I'm going to take that metal and I'm going to add it to this cool water. So this is our hot metal at 100 degrees C. And then I have my cool water at, let's just say, 25 degrees C, room temperature. When I put that hot metal in this system, or I'm sorry, in the water, which is our surroundings, the hot metal is going to send heat or transfer heat to the water. So the water temperature is going to increase, the metal temperature is going to decrease, and so I'm going to have two delta T's. I also have two specific heats, the specific heat of the metal and the specific heat of the water. I also have two masses, the mass of the water and the mass of the metal. So the system is going to be the metal. So let me just add that here. So that's this side. The system is the metal. My surroundings are the water, where the water is going to increase in temperature because of that hot metal. So the surroundings are the water. And so you would plug in the information for water on the right-hand side of the equation and setting that to a negative. And then you would have the metal on the left-hand side of the equation. You would plug in everything that you know and then solve for what you don't know. Sometimes that's going to be the specific heat. Sometimes it will be the mass. Sometimes it wants you to look for the temperature change. So you could be looking for any of those unknowns, but you would set the problem up to look like this. And there are some of those problems in your homework. So I want you to be aware of the setup for that equation. Again, that hint is given there. Magnitude of heat lost and heat gained are equal and opposite in signs. That's what this means. Q system equals negative Q of the surroundings. Always remember that we're taking the delta T. We're always, always, always going to take final temperature minus initial temperature. Sometimes that's going to give you a negative temperature, meaning it's cooling off. Sometimes that's going to give you a positive delta T. That means warming up. So those are just some hints to help you as you're going through the problems that you're going to be working on for homework. And that brings me to your assignment. Your assignment is going to be on page 268. You're going to do numbers 42, 47, and 49. You can handwrite these in your notebook and then send me a picture and submit it to the Dropbox. One thing that I want to give you a quick heads up on is the homework that I'm giving now is for fourth quarter. It will be checked. All of the homework will be checked next Friday. So the due date for homework will be on the class page. You'll see it's all due on Friday. It will also be set up in the gradebook. So now you will have it coming up on your calendar so that you will be able to see it. Should help you organize maybe a little bit better as we still are trying to navigate through this online learning. Again, any questions you have, please feel free to reach out to me via email. You can also ask in the forum, because if I don't get back to you right away, maybe there's a student that can help you and answer in the forum. So please keep up with that as well. It's a great way for us to stay connected in these times of doing these online lessons. So guys, I hope you have a really great day. Stay positive, stay inside, practice your social distancing, and I'll see you for our next lesson.